Jnanam paramam dhyeyam. Knowledge is supreme.
We are continuing with tutorial 6 and we are supposed to solve the fourth problem. So, consider a particle in a Coulomb potential in 3 dimension. So, the potential is a Coulomb potential and you have to evaluate the commutative bracket of the angular momentum operator Li and the Hamiltonian. So, here the Hamiltonian will be will have the kinetic term plus the Coulomb potential term. So, let us get started with this. We have to obtain the angular momentum with the Hamiltonian. So, expression for the Hamiltonian, this is the question. We have evaluated such question, but the Hamiltonian was different, the potential term was different. So, the Hamiltonian here is P square upon 2m, this is the kinetic part. Now, the potential is Coulomb potential. So, you have a q square upon 4 pi epsilon naught square root of x square plus y square plus z square. Okay. And this p square, when I write explicitly, is px square plus py square plus pz square. Okay. So, we will start by writing Lx as Lx is or Lz is Lx Py minus y Px. Here we can evaluate first Lx or Ly or Lz. So, first term first, that is, let us evaluate x Py on the Hamiltonian. This term would give us x Py, this is Px, Py, Pz, okay. And we know from our previous experience that only Px term contributes. So, I will write Px square and 2 by m, I have it here. And for the second term we have commutator of plus q square upon 4 pi epsilon naught, commutator of, here you have x cap and py. So, commutator of this would be one by square root of y square plus z square. So, this will be 1 by x square plus y square plus z square. So, here we have the first term, we have seen that consists of px square plus py square plus pz square upon 2m. The second term is the potential term, Coulomb potential term, which is q square upon 4 pi epsilon naught square root of x square plus y square plus z square. And we are finding out the commutator of x cap and py cap with the Hamiltonian operator. So, in the Hamiltonian operator we have two terms. So, correspondingly we will have two separate terms of the commutator. Then this we remember, we can recollect that this was equal to 1 by 2m. Remember this and x cap and p x square commutes. So, we will have commutation of x and p x square, that is 2 I h cross p x cap, and you have a p y. So, the first term is very simple to evaluate. You have a commutator of x and p, position and momentum, which we very well know now. Second term is q square upon 4 pi x naught. So, x cap we will take out because it will not contribute to the commutator bracket. Only term that will contribute to the commutator bracket is py. So, you have py x square plus y square plus z square. Now, there is a small trick involved here. You will have to find the commutator of this expression, and that comes out to be I h cross p x cap p y cap upon 2m. Commutator of this expression will be very simple. You have to apply the momentum operator py on this, and the other time you will have the momentum operator this operating on the momentum operator. So, this will come out to be minus q square upon 4 pi epsilon naught times x into y, operator position operator x and position operator y, upon x square plus y square plus z square the whole raised to 3 by 2. So, this is the expression for commutator of x p y with Hamiltonian. Similarly, you can evaluate y p x on the Hamiltonian. You will get a similar expression y p x on the Hamiltonian. I will get a similar expression minus q square upon 4 pi epsilon naught x cap y cap upon x square plus y square plus z square the whole raised to 3 by 2. Okay. So, this expression we obtain for the Lz part. So, Lz precisely, that is the angular momentum along the z direction, will be precisely 0. Similarly, you can obtain for Lx, Ly and commutator of Ly, commutator of Lx with h to be 0. So, we have to also do in the second part what will be the list of maximum or maximal compatible sets. So, what you can think of is one more thing you can or you have seen, commutator of Lz with L square is 0. So, and you also know this relation I h cross Lz. In general, this is Li Lj IH cross epsilon I j k L k. This expression you know, when you make a cyclic rotation you will have 3 commutation relation which will result in Lx, Ly or Lz. So, all these are right, I am writing because we want to find the maximal compatible set of operators. So, since Lz and L square commute, they can form a simultaneous eigenkit. Similarly, here you have seen that these Lz and the Hamiltonian operator commutes, so they can form a simultaneous eigenkit. However, Lx and Ly or any of these Li and Lj, they do not commute. So, one cannot obtain simultaneous eigenkit for these operators. However, when you obtain Lx, when you operate Lx with L square or Ly with L square or Lz with L square, you can have a simultaneous eigenkit because these Li's with L square commute. So, the maximal compatible maximal compatible group or set of operators are L square, okay, that is L, Lz and H. You can very well write here Lz instead of Lz, you can also have or you can have Lx and Ly. You can have a compatible set of L, Lx, H or L, Ly and H. So, these form the compatible set of operators, and these operators can be such that when you pair them you can have a form a simultaneous eigenkit for these operators. And we have seen in the tutorial 5 some example wherein you had 2 operators which commute. So, the eigenkit obtained by one operator say B was the simultaneous eigenkit of operator A. In the previous problems we have seen such examples. So, this was problem 4. Problem 5, I think part of it was done in the class, that is one needs to know how to derive this Schrodinger equation in polar coordinates. It is very interesting to get the result which is given in the question, that you can try by writing the Cartesian coordinates in terms of polar coordinates, and when you rewrite in polar coordinates you obtain this Schrodinger equation which is a function of R, capital theta and capital phi. So, if the wave function in the radial part, let us substitute psi, we are given r, theta and phi as a e raised to minus r by a. This is given with, we will assume that L is 0. So, let us simplify that L is 0. So, when L is 0, n can take value 0 to 1. So, n, we assume n is equal to 1. Okay. And now we will also require these gamma function integral, So you will be using this, which is nothing but p of gamma of p, and p plus 1 is greater than 0. So this is we are going to use. So we will try to evaluate or substitute the wave function for the ground state. So when you substitute the wave function in the radial part of the equation, you have the first term is 1 by r square d by dr of r square, and in the wave function you have a e raised to minus r by a. So, e raised to minus r by a, okay, r square d by dr. So, r square d by dr, this is the first term. The second term is cross square e plus e square upon 4 pi epsilon naught r. So, this term will remain untouched. So, I have a e raised to minus r by a is 0. So, this you can easily do. You have to take the derivative with respect to r. This will give me minus a, and I will have derivative with respect to r square. Here you will have minus a, okay, upon, in the previous term we had a upon r square. So, let me write a upon r square, and derivative of e raised to minus r by a, I will have a term. So, I will have a minus sign, then I have d by dr, okay. First term I have r square e raised to minus r by a, okay. So, again this is a by r square, derivative of e raised to minus r by a will give me minus 1 by a. So, I write here minus 1 by a, and I have derivative with respect to r square and e raised to minus r by a. So, this we have to evaluate, plus 2 m upon h cross square into E, where E is for the ground state, n is equal to 1, plus E square upon 4 pi epsilon naught r times the wave function. The wave function is nothing but a e raised to minus r by a. So, this will be a e raised to minus r by a. I will write downstairs. This entire thing is equal to 0. So, I have here minus a by a r square, derivative of this I will have two terms. So, I have here 2 r, I will have a e raised to minus r by a minus r square by a times e raised to minus r by a plus 2 m upon h cross square. This term will remain as it is, it will come down because there is nothing to operate on. This is E plus E square upon 4 pi epsilon naught r times the wave function a e raised to minus r by a, which is 0. Now, in the next step we can actually take these wave functions out. So, I have a, I have to take a out. So, I will have 2 minus 2 pi r first term times a, then the next term will be plus 1 by a square, because r square will get cancelled. So, I will have first two terms of the first term plus I will have 2 m upon h cross square E equal to 1 plus E square upon 4 pi epsilon naught r times the wave function. So, this entire quantity is equal to 0, this coefficient is equal to 0. So, here what we do is we will try to simplify this further. So, let us or rather this is possible only when if this term is going to 0, that is I can take h cross square upon 2m times this expression, this goes to 0, this expression times this part. Okay. So, when you simplify this, if and only if A, okay, if and only if A is equal to 4 pi epsilon naught r upon m E square. So, this is possible only if A is 4 pi epsilon naught r upon m E square. So, what we have done here is that if we have assumed that this quantity is nothing but 2 by r, okay. This entire quantity is nothing but 2 by A. Okay. So, we have got a relation with respect to of A in terms of E naught. Okay. So, what we have assumed here that this quantity is equal to this term. Okay. So, with this we have A is 4 pi epsilon naught upon r upon m E square. So, from this if we substitute for A, we will be able to obtain the value of energy, the ground state energy. So, we have to substitute. So, after substituting, again this is nothing but Bohr radius. Okay. Okay. Now, we will get the value of the ground state energy is given by, from the previous expression we can get this as 2m A square. Okay. So, this will be the expression for the ground state energy. Fine. Now, we have obtained the ground state energy, we have obtained the value of small a, we have to obtain the value of capital A. So, capital A we can obtain by taking A is a normalization factor, capital A. So, by performing the normalization condition, using the normalization condition, that is integral over r theta and phi. So, r theta and phi, r goes from 0 to infinity, theta goes from 0 to pi and phi goes from 0 to 2 pi. So, when you integrate r theta and phi, that is psi square r theta and phi, okay, this is psi square r square sin theta d theta d phi, and you have a dr also. Okay. This should be equal to 1. So, we know what is the value of the wave function given to us, that is a square exponent of. So, we will on simplification, we obtain what do we obtain? Value of capital A as this. You can check, it is not difficult, and I have given you the hint. You will just substitute for psi square, which is A square e raised to minus 2r upon A, and then you integrate over r square. So, integral over sin theta d theta will give you 4 pi. So, this integral will give you 4 pi, and the remaining integral is r square e raised to minus 2r upon A, and you have to use the gamma function. This will simplify A to this. So, please check this, it is a simple integration, and in the next part we are asked to find out the mean distance. So, again this B part is to find out, in the B part you have to find out the mean distance. So, the mean distance is the average, which you can easily do is psi square psi star r psi, very simple expression. So, it will be 4 pi a square 0 to infinity. When you take psi star r psi, you obtain r cube e raised to minus 2r upon a, which is into dr, which is nothing but 3 by 2 times a. So, this is the mean distance. So, mean distance is one thing you have to evaluate, the root mean distance and the most probable distance. These are the 3 quantities you have to evaluate for the electron in a nucleus in the ground state. So, this was the mean distance, this is the mean distance, okay, which was obtained by mean distance. How I have evaluated? Psi star r psi dr, as simple as this, 0 to infinity. Okay. The next part is the mean square distance. This also you can evaluate. Mean square distance will be r square, that is 4 pi a square 0 to infinity. Now, you have a r square. So, this becomes r raised to 4 e raised to minus 2r. Again you will use gamma function and get the result for this. So, this comes out to be 3 a square. Okay. Mean square distance comes out to be 3 a square, and you can similarly calculate the most probable. The most probable distance is given by what we have to do is we have to maximize this quantity, that is psi star r square psi star psi. So, you have r square minus 2r upon a. So, when you maximize this, this will lead to r equal to some or r prime equal to some a, and then you can obtain for that particular value of r or r prime, we will have the most probable distance. So, the most probable distance, let us call it as some r prime. So, that r prime is given by maximizing this quantity. When you maximize this quantity, this will lead to r prime equal to a. So, the most probable distance is equal to small a, which is nothing but the Bohr's radius which we have evaluated. So, with this end of this part, third part is actually you have to calculate the classical and quantum mechanical probability for R greater than 2a. So, that is a easy check. You can just do it for R greater than 2a. So, when you put the limits, your limits will be from 2a to infinity. Instead of 0 to infinity, your limits would change for R greater than 2a. Your limits of integration will be from 2a to infinity when you calculate the mean value. Okay. So, classically and quantum mechanically you have to evaluate. For quantum mechanically you will integrate from 2a to infinity for the expression, and it is very simple. So, this would come out to be something like 13 e raised to minus 4. So, please check this if it is correct, and with this we end this tutorial, and we will have more problems on harmonic oscillator or hydrogen atom. Based on these problems we will have further tutorials.